enough? Let me bring my screen up.
I hear you just fine, Art.
Okay, good.
Take it away.
Where am I? How does this work? Can you still hear me?
Yep.
Ah, here we go. All right. No, not that way. Stop. I don't want to edit it. I want to show it, don't I? Here we go. Okay, what we're talking today about is a simple Arduino device that utilizes a GPS to show the time in our recordings of occultations. It's a very simple device. I think you'll probably like it. This is a little tricky to explain some of this stuff because on the one hand, I have to show you how to do the technology without telling you much about how to do the technology. But I hope just to give you enough to get you started on it, and you're all technologically capable people, so I think you'll be able to figure out the rest if I just give you something to start with. At least let's hope so. Okay, what this device does basically is it makes precisely timed flashes that are recorded on an occultation video. And subsequent to that, when we play back the video via PyMovie and IOTA, the times of those flashes will be measured and then interpolated to the DNR events that we're trying to time. So the idea is very simple, and a lot of these have been made before, not a lot of these, but these have been made before in various flavors. And this is one that I built a couple of years ago. This is basically what we're talking about. This thing at the bottom is an Arduino with what's called a GPS shield on top of it. It's being powered by one of these little power supplies that you use to charge your phone battery. And obviously coming out of it is a wire with an LED at the end. And I just happened to catch this as it was flashing. The flashes are rather long, they're a second long. But what we're talking about is this device here. It's a sandwich of two things. The Arduino's at the bottom and this GPS shield is on the top. And I'll point out some of the features of it here. This is the actual GPS receiver right here.
I'll let you know.
This one has an integral antenna on the top. This is a little SD card drive, if you want to call it that you can put one of these small SD cards in, which will either read or write data. This is a backup battery. I'll talk about that in a minute. These can be, oh, here's the SD card that goes into this slot, obviously. These can be powered by either USB 5 volts, as this one here is. It can also be powered via this socket down here with the 12 volts that we use for our cameras and the IOTA VTI and all that sorts of equipment. So it's very handy power-wise. Now, why is this useful? It's a reliable and inexpensive way to add the times to an occultation recording. It works all over the world, wherever GPS is available. There's no need for any kind of phone service, a computer, you don't need internet, you don't need NTP, you don't need WWV. You don't need subscriptions to anything. Everything is public domain. And it works in the optical path. So the same thing you're looking at, your occultation event, the stars and asteroids, will have this information embedded in the same image. So we don't have to worry at all about what's happening electronically in the camera or with the VTI. There are no errors involved with that. So I'll explain for a second briefly what an Arduino is. Basically, it's an open source microprocessor board. Open source means anyone can copy it and make money by selling these things. And it uses public domain software that anybody can use and play with. There are very, very many variants and clones. It's a huge community. And here are some of them. This one on the right here is the original official Arduino. It's made by an Italian company. This was developed in Italy at a university for their students to develop microprocessor hardware and software. This one here's that 12-volt power socket. These have sort of an old-fashioned USB connection. This is USB type B, I believe it's called. It's crystal controlled. Here's the microprocessor itself. And it has two banks of headers. These are referred to as headers. They're stand-up sockets, basically. This piece down here has voltages and ground and so forth. These few here are analog voltage inputs. And these are all the digital inputs and outputs, the GPIO, general purpose input and output sockets. That's where we'll get all of our data from. This one on the right is a clone of this. This is made by SparkFun. It's referred to as the Red Board. It's essentially the same thing. It has a slightly more modern processor. It's surface mounted here, but the pinout's exactly the same. This one has a smaller USB connector, which is sometimes handy. But in other respects, it's exactly the same. These come in various form factors. This shows two of them. This is the standard size. This is the standard size. This is a nano. This is, again, an official Arduino device. And it's about the size of a man's pinky finger. Again, small USB. This one doesn't have a 12-volt socket, although it can perhaps be powered by 12 volts through these pins. I'm not sure about that. But it's handy if you want to put something in a smaller package. Okay, what an Arduino does is it takes inputs and processes these inputs being voltages or currents or something like that, and makes outputs based on these inputs and processes that you tell it to. And they can do many, many, many things. For example, you can measure temperature, turn on a heater, you can measure motor RPM, you can tell whether your Segway is vertical or lying flat on the ground and adjust the motor speed so that you don't fall down, that kind of thing. What we're going to use here is to get the very precise time from a GPS receiver and then flash an LED so that our video recorder can see that. So GPS, you already know quite a bit about GPS, but what a lot of people don't realize is that from its very beginning, it was designed to provide time distribution. This was recognized as a problem many decades ago. And so when GPS was developed, this was integral in to its functionality. Very wisely, the developers made it all public, at least the non-military secret stuff, of course. So it was very quickly developed, and nowadays, of course, we use GPS in many, many circumstances. And because of this, there are many GPS devices, and many of them do work with Arduinos. And here are some of these. That was a note to myself at the bottom, reminding me to take a picture with the antenna added. So these are what are referred to as shields. A shield is a device that sits on top of those headers on the Arduino board. And the pin out and spacing of those pins is designed to fit on there. This device here is a very nice GPS board made by Adafruit. That's the one I use the most. And these are copies, essentially, of that. This one uses the same receiver as the IOTA VTI, a PA6H receiver, which is very nice. Has an integral antenna on the top. This one here uses a U-Blox Neo. This is the same receiver that's used in the QHY cameras, the GPS cameras. It does not have an integral antenna, so with this one you have to use this external antenna. Here are other copies. This one is made by Fast Tracks. I haven't used this one yet. I just found it on eBay some time ago and I bought a bunch of them, but I haven't used them yet. These smaller ones here are referred to as breakouts, and they're just little breakout boards with pins on one end that you can plug into various things. They're not designed to fit on top of an Arduino like these bigger ones are, but essentially they have this exact same functionality. So this has the same receiver as this, has all the pins that we need. This is a version that uses that PA6H receiver. that this one has, and this one has that U-Blocks receiver that this one and the QHYs have. Most of them have these UFL antenna connectors, which I don't care for very much because they're very fragile. This one here has an SMA connector, one of those screw-on connectors, which is very nice, much more sturdy. Okay, so what we're going to do is mount this shield on top of an Arduino and then program the Arduino to do what we want. That's what we're after. So here you see the shield, as it's called, and this is just the name, I suppose, refers to the fact that it shields the Arduino board from view. In the Red Hat world, I'm sorry, in the Raspberry Pi world, these are referred to as hats instead of shields. So someone got, you know, the idea that whimsical names were clever. But you can see how it fits. The pins line up exactly. And then down here is where the connections are made. On the bottom of this, and this is something you have to point out, when you get into the Arduino world, you do have to do some assembly. Some assemblies required, as they say in the IKEA stores. Okay, for most of these, the major parts are already soldered on the boards, of course. It's all surface mounted stuff. But the headers on the edges and any other wiring that you might need, you'll have to connect that yourself. So you'll have to acquire a soldering technique. It's not hard to do, of course. Many of you have pretty much done a lot of this already. But if you can't get, you know, if you can't be bothered with this, find someone to do the soldering for you. It's the only difficult step, in my opinion. Here I have a strain relief. It's just a piece of copper wire that is passing through these holes here. This is just a general purpose breadboard area where you can mount other things if you happen to need them. But I just use it to fasten the wire to so that this LED on the end of it doesn't pull out of its sockets there. But once the whole thing gets packaged, it's very sturdy and it's pretty stable. Okay, now you've got the thing physically put together, and like I said, there's a bit of work in the details, but you know, you can figure those things out yourself. But here we're going to get into some of the weeds. What we're going to do here is put code, the actual programming code, into the Arduino. And to do this, we need to load the Arduino IDE. This is the integrated development environment, into our laptop or computer. You download this from this address. It's free. It's very stable, and there's nothing you have to worry about. When you've loaded it on your computer, you'll see it'll come up as an icon. You click on the icon, it'll open up something like this. And what this is what's referred to as a sketch. A sketch is a simple program. The programming language in Arduinos is C++, which is a very common programming environment. There's a lot of things in our world that run under C++. I think a lot of the software that we use in our work uses it. Anyway, the programming code is, again, whimsically referred to as a sketch. And a basic sketch in Arduino works like this. There's a setup area where all your variables and things like that you need to assign one time. That happens up here in the setup area. And then there's a loop area where the stuff that needs to be done repeatedly is placed. So the setup happens once, and then when all your variables are set up and functional, then you go down here into the loop area and it does all of that stuff repeatedly. And what we're going to do is sample the GPS receiver, get the time out of it, and then tell it to flash these LEDs as we want to. Okay. So the code that does this, I've already developed, and you know, I'm constantly working on this thing, so I'll probably update this. But right now, there's a functional version of this LED flasher in our IOTA group space. There's a file section in there, and there's an area called Aart's Arduino timers. And in there, there's a file called ledsd.txt. So you copy this, and you paste it into that IDE that I just showed you, this one. You just paste it in here. You replace this default sketch with the sketch that's in this text file. And what happens is that you'll see that text replaced with this. Okay, it's a big long thing. It's, I don't know, maybe 30, 50 lines. Actually, there's a lot more lines because at the top of every sketch that I put in that file directory, there's a lot of explanation telling you how this particular sketch works, what it does, how you wire the device, how you input data into the device, how you use the device, and so forth. So I can't show it to you here. You'll have to figure all that out yourself. But my point here was just to show you sort of how to get the code into the Arduino. Once this is loaded, you should save it with the proper name so that you will identify it and you can find it later on. And I'll warn you, you should not save it in the Arduino directory. The Arduino IDE software is loaded in a particular directory under the program's x86 directory in Windows. I don't know where it goes in Macs or Linux devices. Arduinos can be programmed in those other environments as well, I should mention that. I'm only familiar with Windows. But you have to be careful not to put it in that Arduino directory, because if you ever update this, this IDE environment, what it does unhelpfully is erase everything in that directory and then replace it with new software, new IDE software. And if your sketches are part of that directory, the subdirectory, for example, they'll disappear. And that's happened to me in the past. So anyway, you give this a proper name and save it. You can save it in your documents directory or wherever. Wherever you save it, or the IDE subsequently will be able to find it. In addition to your sketch, the stuff that you've entered, and that in the future I'm hopeful and confident that you'll be able to code yourself. In addition to those things, there are libraries that Arduino uses that assist your sketch with its processing. And libraries are utilities that do special things, like though in our case, they're going to read the data from the GPS receiver. They're going to tell which digits of an LED display to turn on and off and that kind of thing. There are many other libraries, and typically a sketch will only need a couple or three of these. Some of them come with the IDE distribution that you've already loaded on your computer. Others you have to find and download yourself, okay? When you download them, you can put them in this library folder here, and the Arduino will know where to, the IDE will know where to find them when it needs them. Again, there's a little bit of work and learning involved. I don't want to get into the details too deeply. Okay, now we're going to actually load the code into the Arduino device. You do this via the computer's USB port. Then you tell the IDE. Let me go back to where this is. The IDE has this tools submenu here. When you click on this, and this is not an active display here. When you click on this, you'll see one of the things will let you select your IDE port. I'm sorry, USB port. So use that tool menu to select the USB port. And after that, your computer and the IDE will remember what port that is. You won't have to do this again. On that Adafruit GPS shield, that blue colored shield on top of the Arduino, there's a switch. And you have to switch that to direct, which directly connects the Arduino to your computer via the USB. And what you do then is click the right arrow button below edit. Let me find this for a second. That's this button right here, this one. And what it will do is we'll compile your code that you've just copied in there, make sure the syntax is okay, and then download it to the Arduino, okay? When you're done with that, you take that switch on the GPS and set it back to soft serial. That's just the way it's labeled. And what that does is it connects the Arduino's serial port to the GPS receiver, okay? And then you're done. You're done with programming the Arduino. And from now on, it will execute the code you've entered into it forever. You can change it, obviously, but it won't, it's not volatile. It will not disappear when you turn the device off or unplug it or put it in a drawer for 10 years. You can come back in 10 years. It'll still have that code in there. It's written into flash static memory, so it won't disappear. I suppose if a cosmic ray event, hits us real hard, it could damage it, but I haven't had any trouble with that so far. It's very robust. Okay, now the thing is programmed. Now we need to connect an LED with the current limiting resistor, of course, because LEDs are current devices. Remember the picture back here? You have to connect the LED and the instructions for what pins to connect it to, and what these other connections are. These wires here, what they're connected to is described in that text at the top of the sketch text file. All this stuff here is descriptions of all that. The Arduino is ready to go. GPS is functioning. If it's powered up, you'll see it start working. But you want to tell it at this point what to do, okay? In the sense that, okay, I have an event happening at some point in the future. I want this to flash before and after the event. That's the whole point of this. What the code does is it looks at the time, of course, the date and time of your event, and it will attempt to place or will place flashes of light at some half interval. This is your whole interval before and after that event. So if the event happens at 16:37:43 or is expected to, you want 2 flashes separated by 30 seconds. So 15 seconds before the event, 15 seconds after the event. Okay, that's what this input information is. And you write this on the very first line of your SD card. You can also add on other information about where your station is and so forth. You put the GPS card into the slot, and at that point, the Arduino is fully operational. It'll start working. In other words, it'll wait for that time, your event time, and place flashes before and after that event.
Art, quick question.
Yes?
Is that information, do you need to put that information into a file on the SD card?
Yes.
Does
Yes,
that
that's
file
right.
have a particular name?
Yeah, input.txt.
Ah, okay. Thank you.
Yeah. So that's written up in the directions. All of that
I
is
see.
detailed in there.
Okay, thanks.
Yeah. Now, in addition to those flashes before and after the expected time of the event, the Arduino will also flash at every minute, at the 0 second of every minute. And when it's done, as it makes all of these flashes, it'll actually log that time. So here, for this particular event, this, you'll remember, was the information we input at the beginning. We're now after the event. You've set it up outside and it's working and so forth. You've finished collecting your data. You capture that file, and this is what will appear on that file. That same input.txt file. Sorry. So here's the time of a flash. It's at the time 16:34. Here's your looks like longitude and latitude. This was data from Adelaide River, Australia. A minute later, another flash at 16:35. And these times are very precise, by the way. It's good to at least 5 digits of zeros. About 10 microseconds is the precision of this flash. It's very, very good. And anyway, it does that every minute and makes a flash. And then when the first so-called goalpost flash, one on either side of the event, happens, it'll make a flash at that requested time. So this is the first one of these. Remember, we requested the event to be 15 seconds on either side of 37:43. So at 37:28, it made a flash, and 30 seconds later, at 37:58, it made the second flash. And then it continues with its per minute flashes until you come and collect the device from your station. one other thing, the minute flashes, if they happen to fall between the two, excuse me, goalpost flashes, will be omitted, just so it won't interfere with the actual event. Okay, I'm rushing through this a little bit. I'm running late on time. So anyway, I'll show you what the flashes do. The flashes are seen as spikes in the background light level, and these are measured by PyMovie. Then you know what the flash times are, and so you enter those into IOTA, and then IOTA can interpolate between those to measure when an event happens. John Moore did this for an actual event last October, and he provided me with his light curves. And let me explain what these spikes are. So these spikes are the light flashes produced by the Arduino GPS system. Obviously on the bottom here is your actual occultation. This is one of the per minute flashes. This is one of the first goalpost flash before the event. This is the second goalpost flash after the event. This is another per minute flash. And over here is another per minute flash. Now there should be a per minute flash right here, but because it's in between these, that one was purposely omitted so that it wouldn't interfere with the expected time of the event. These, as I mentioned, are very, very precise. They're very short. And you can see that they do contribute to the noise and to the background scatter. And this is an area where, as Richard Nolthenius mentioned yesterday, it would be nice if IOTA could exclude these areas from its noise measurements. But that's for another discussion. So John actually compared VTI time measurement against this flash system measurement. And he selected these times here to use as his interpolation start points. And I won't go into the details here because I don't really know them. I don't know what he did, but IOTA has special special procedure for interpreting these flashes and can interpolate between them to find out when that event disappearance and reappearance are. And it does a very nice job. And here from John's actual measurement comparing VTI versus the flashes are the results. And you'll recognize this as part of the IOTA log at the end. It doesn't typically have two lines here. I simply copied a line from the flash log and added it to the below the line for the VTI log. And you can see that the numbers are very, very good comparisons. They're within a couple of hundredths of a second of the VTI time estimate. Here's the D time and the R time. The error intervals, the confidence intervals are exactly the same because those are based on the actual light curve itself. But the times are very good, and it's a very good system overall. That SD card is actually optional. After I did this and went to a bit of trouble to program it in there, it occurred to me that we already know what the flash times are going to be. We already know what the station location is, presumably. So we don't really need the SD card. We can just avoid fussing with it, and it's a little bitty thing. And I wouldn't use it in the dark at night. You know, I'd preload my Arduino with this at home before setting it up. But it's easy to avoid using this. So you can actually hard code the event information. Since it's so easy to program an Arduino, it's not at all difficult to add this line to the code. And then for this version of it, I'm using the same terminology that ArtCodeWatcher uses. So date, time, duration, and expected or possible time error. And it uses duration and possible time error to create an interval for you on either side of the event. So you don't have to worry about what that interval is or whether it's a whole interval or a half interval. It calculates that for you. So anyway, that's not in the current version that I have in the IOTA group file section, but I'll probably add this version to that so you can actually drop the SD card if you don't want it. It's still nice to have because it is a proper log of what actually was took place. But once you have confidence in the system, you don't really need it. All right. So this is my final implementation. It's sort of, you know, half-baked and sloppy, but it's perfectly robust. And these things, once these two cards are sandwiched together, they're pretty sturdy. And once this wire is fixed in place, it's not going to go anywhere. So plug it in, put it in a baggie, hang it on your telescope with a clothespin, and you're done. That I think it'll work fine. These receivers, by the way, are so sensitive. They'll work sideways, they'll work upside down, they'll work underneath some stuff. So they're actually pretty good. You don't have to be too fussy with them. This is John Moore's implementation of it. He made a proper box for his. He 3D printed this. He has a 3D printer, and he put his LED in a ping pong ball so that the light is diffused. But there you go. I think that's the end of that one. Any questions?
Steve here.
Yes, Steve.
Hey, Art. I was just going to suggest that it might be good to recommend to people that they always let the device, that they start it up at least 15 minutes prior to the event, give it at least 15 minutes to make sure it's collected a full almanac before it starts doing any timing.
Yeah. Well, of course, these do have batteries, and the batteries will retain an almanac. And the almanac isn't as important as the leap second offset, of course.
Right, right, which is what that's right. And that's what I'm thinking of. It's always best if you give it 15 minutes to ensure that there's no issue there. Even if it's saved the data via the battery backup, you still could have an issue in some, you know,
it's
crazy
always a good idea.
situations.
I agree. But the batteries do work for quite a long time.
Yeah, well, they work, but you have these, you have some potential race conditions, right? If you happen to be recording right before a leap second happens, you know, they may not know that a new leap second is coming up because the almanac thinks it's right when in fact it's getting ready to change. So
Sure.
it's always best to, the safest way to do it is to ensure that.
So
Now
Art,
the thing is, leap seconds might go away. I suppose many of you know that there's a lot of political and commercial pressure to get rid of leap seconds because they cause a lot of issues with computing and, you know, high-speed trading and that kind of stuff, and aircraft safety. So there's a lot of pressure now to get rid of leap seconds. And so we'll have to deal with that. I'm sure Dave Harrell will spend a lot of time on this if it ever happens. But I think that's pretty imminent that they're going to just drop it. What I've read.
Art,
Yes.
this is Bob Anderson. I
Yes, Bob.
have two comments. Dave Galt and Tony Berry, and I have confirmed by actual experiment, will tell you that the 1 PPS signal, which I assume you're using to time the edge of your flash, is sort of reliable, but it can go away. I think what makes it go away is when the overhead constellation changes, and that can cause a momentary loss of lock. And a scheme that you might consider, which I have used successfully, is to use a digital phase lock so that you don't use the 1 PPS signal directly. Instead, you've got a very reliable and stable crystal. You can use the microprocessor timing and just lock it, phase lock it to the 1 PPS signal. In experiments that I've run here, I've been able to let the 1 PPS signal go away for up to 20 minutes without losing more than about 20 microseconds of timing on the edge. So that's just a refinement that you just might consider. The other comment is that IOTA, in analyzing the flashes, expects that you have adjusted the intensity of the light so that you have not saturated your camera. If it has been saturated, the interpolation algorithm that IOTA uses will not be as accurate as it could be. In experiments where I very carefully made sure that saturation didn't occur, I could get correlation to the IOTA VTI and my own flash unit to within a few microseconds, actually. 10 microseconds was very common. But if I allowed saturation to occur, I began to lose that. So I think that's good advice to users of your device.
Yes, thank you for that. John Moore made an actual working device. Mine is sort of a breadboard, tabletop model. But his actually has a potentiometer to adjust the brightness, which I think is a really good feature.
I'll add one more comment on the idea of using a phase lock loop. It's a good option, but it also means you need to be careful about ensuring that you need to track how long it's been since your last GPS signal, because you don't want to necessarily trust your phase lock loop to work for, say, 2 hours after the last PPS signal. So you need to have the approach Aart has taken is susceptible to dropout, in the sense that if something drops out, you potentially lose that timestamp. On the other hand, it's also very reliable in the sense that the flashes you see, correspond to actual flashes, and you don't have to worry about, whether or not your loop may have lost track over time or anything like that. So
yeah, right.
There's kind of.
I have found, though, that while the chip is reacquiring lock, that the 1 PPS signal may not necessarily occur on a 1-second boundary. I've seen it.
It could be. Yep. There's some advantages to watching for that as well.
I've seen it jitter. Now, I don't know if Tony Barry is on the call. I thought Dave Galt was. And these guys have just made an immense number of measurements, so
Sure.
They probably should chime in here. I benefited from my interactions with them when I was doing some of this work, which is how I became aware of and began to study the effect. Now, as I agree with what you say, Steve Preston, but there's a nice log there that Aart is putting out, in which he could just indicate that we're depending on the stability of the phase lock loop. And provided that you had lock before an event, there is the stability of those crystals means you can carry through any event of any reasonable size with great confidence.
Yep. Now, my understanding is that the PPS is actually not generated by the satellites. PPS is created by the receiver.
Yes.
And the receiver actually correlates a whole bunch of satellite signals and then, steadies that. But so probably the receiver already has the functionality of a phase lock loop, because it's got to produce that PPS independent of the satellites.
It doesn't.
And in my experience, I haven't really found that the PPS goes missing any time. Maybe I just haven't observed it long enough, or taken long enough data.
You have to look at it. You have to look at it long enough.
Yeah.
I haven't found a good explanation written up anywhere, but I just assume that it's a change in the overhead constellation. And momentarily, the chip says, I don't have enough satellites in view, just sort of uneasy about it. And it is no longer able to extract the relevant information to generate the 1 PPS signal.
I see.
Generally speaking, if the receiver's got a good look at the sky, you should have no trouble. But it's only during startup where that you get most of the problems.
Yeah.
I've measured it over a period of 3 days, and I've had 2 dropouts when I was running it for 3 days steady.
Oh, okay.
So it's infrequent, but it is possible. And it was enough for me to put the little extra work to not use the 1 PPS interrupt directly, but instead use it to synchronize one of the microprocessor timers and use the interrupt from that timer to run the LED. It is a subtle refinement. I know it's not in the IOTA VTI, and I'm not suggesting that you should put it in there, because it doesn't seem to be that big a problem. But
I think the IOTA VTI does use phase lock loop.
Um,
Dave can confirm. I think they are looking to be using the PPS to train an internal time base.
yeah, I think that's correct. Where's Tony?
Well,
Tony.
that's great. That's great news. I was unaware of it, but I'm really
But
glad to hear it.
IOTA VTI keeps the track of the 1PS and raises the flag if it's out of sequence.
Right.
So it brings up an error.
We may not be able to solve all these issues at this time. We're getting behind, and I think we need to move on to the next presentation. I want to thank everybody for their input on this, and it may be that we're going to have some further discussion online.